On to section 3.4, and there's quite a bit in this one, so this is going to take more than one day and more than one video, but let's get started. Remember when we were solving quadratic equations, and it turned out that some quadratic equations, or some degree 2 polynomials, didn't have any solutions in the real numbers. So if you just have real numbers, there's no solution to an equation like this. Because if you try to use the quadratic formula, you end up with the square root of a negative number in your solutions. So an equation like this does have solutions, but they're not real numbers. They are complex numbers, 3 plus 2i and 3 minus 2i. So we had to expand our number system to include the complex numbers so that all quadratic equations had solutions. So when we have all the complex numbers to work with, then every degree 2 polynomial has at least one zero. Every quadratic equation has at least one solution, and most of them have two different solutions. They might be real numbers, or they might be complex numbers involving I. So now that we've gone on to start talking about polynomials of higher degree, what if we had a degree 3 polynomial, or degree 4, or degree 7? Is there a possibility that it might not have any solutions, or that we might need to expand our number system even further and include more kinds of numbers to allow polynomial equations like that to have solutions? Well, the answer happily turns out to be no, we don't need any more numbers beyond the complex numbers. Once we have the complex numbers, we have all the numbers we need to solve any polynomial equation of any degree. And in fact, that fact is known as the fundamental theorem of algebra. Every polynomial function of degree 1 or more, whose coefficients are all complex numbers, so they could all be real numbers, or you could have complex numbers involving I as some of the coefficients, but every polynomial function has at least one zero in the set of complex numbers. So let's look at an example so we see what that means. If I write down a polynomial of whatever degree, here's an example, 4x to the third minus 15x squared minus 31x plus 30, that's a degree 3 polynomial. So the fundamental theorem of algebra tells us that that polynomial must have at least one zero. It doesn't tell us whether that zero is a real number or not, but it has to be some sort of complex number. Now, it turns out that this particular polynomial has 5 as a zero. If you plug in 5 for x, it does come out to equal 0. Or if you do synthetic division, divide by x minus 5, which means you put 5 out in front and you work through the synthetic division, you do get a remainder of 0. So 5 is a 0, x minus 5 is a factor, so you can factor out x minus 5 times the other factor is the quotient we got, which was 4x squared plus 5x minus 6. But now that 4x squared plus 5x minus 6, that's a polynomial of degree 2. So the fundamental theorem of algebra applies to it and says that it has at least one zero. Turns out that negative 2 is a zero of that polynomial. So we can go through the synthetic division, get a remainder of 0. We know that for the 4x squared plus 5x minus 6, one of the factors is x minus negative 2, or x plus 2, and then the remaining factor would be the quotient we got there, 4x minus 3. Now 4x minus 3, that's a degree 1 polynomial, and the fundamental theorem of algebra applies to that and says that that has at least one zero. In fact, 3/4 is a zero for that. So we can take that, pull out a factor of x minus 3/4, and what's left is just the number 4. If you multiplied that back through, you would get 4x minus 3. So now we've got a 4 times an x minus 5 times an x plus 2 times an x minus 3/4, which is the complete factoring or breaking apart of that degree 3 polynomial that we started with. So that degree 3 polynomial turns out to have zeros 5 and -2 and 3/4. So it turned out that it had 3 different zeros. And when we pulled it apart into these factors, there was one of these factors, x minus some number, for each one of the zeros. 5 was a 0, x minus 5 was a factor. -2 was a 0, x plus 2 was a factor. 3/4 was a 0, x minus 3/4 was a factor. And that sort of thing is true in general. That's what our book calls the linear factorization theorem. Every polynomial function of degree n greater than or equal to 1, so n just stands for whatever the degree is, whose coefficients are all complex numbers, so they might all be real numbers or they might involve I, can be factored into the form a sub n times x minus c1 times x minus c2 times and so on. So there's as many of these x minus something factors as the degree of your polynomial. If it's degree 5, there's going to be 5 of these. So these numbers, the c1 and the c2 and so on, are the zeros of your polynomial. They are complex numbers, which means they might or might not be real numbers. They might be something nice like 5. They might be a fraction, they might be irrational, like the square root of 17, they might be imaginary, but they're some sort of complex numbers. They're not necessarily all different numbers. You might have some numbers showing up more than once. And if they do, we just say that they have multiplicity of however many times that shows up on the list. And then this number out in front, this a sub n, that's the leading coefficient of your polynomial, and it's not one of the zeros. So, for example, if f of x in factored form is 2 times x minus 9 times x minus 9 times x plus 4 times x minus 1/2 times x minus the complex number 8 plus 5i times x minus the complex number 8 minus 5i. 2 is not a 0, but 9 is a 0. X minus 9 is a factor, so 9 must be a 0. Notice that if I plug in 9 for x, then here we're going to get 9 minus 9, which is 0. And then that 0 times whatever else we have is going to come out to be 0. So 9 is a 0 because of x minus 9 being a factor. And x minus 9 shows up twice, so 9 is a 0 of multiplicity 2. You can list it twice on the list of zeros. X plus 4 is a factor, so -4 is a 0. X minus 1/2 is a factor, so 1/2 is a 0. X minus 8 plus 5i is a factor, so 8 plus 5i is a 0. And x minus 8 minus 5i is a factor, so 8 minus 5i is a 0. And altogether, there are 6 of these factors that involve x, that are made up of x minus some number. So the degree of this polynomial is 6. If you multiplied all of this out, it would involve a term that had x to the 6th power. In fact, down here at the bottom of the screen, I'm showing what you actually would get if you multiplied it all out. Now, actually doing that would either take a lot of work or it would take the help of some sort of computer software. But if you multiplied this all out, assuming I didn't make any typos when I typed this in, this is what you would get. It would be a degree 6 polynomial, and you can plug in any one of these numbers for x and evaluate and get 0. Now, I'll just mention in terms of the fundamental theorem of algebra and finding solutions to degree 3 and 4 and 5 and so on polynomial equations, there's some interesting mathematical and historical background there that I'm not going to get into in this video, but I have posted on Canvas a few supplemental videos that you can look at if you want to. They're not required, but they're kind of interesting things to go along with what we're talking about here in class. So I'm going to end this particular video right here, and then we'll follow up next time with some specific examples and some facts and theorems and things that we can use to help us figure out what the zeros or what the factors of some polynomial might be.